In the previous video, we covered the history of Ethernet and how spanning tree came to be because we invented the transparent learning bridge. And in order to support the inherent capabilities of original Ethernet with broadcast and multicast, we need to flood with the switches. Because we're flooding, we're susceptible to loops, and hence we need spanning tree to break loops. In this video, we're going to explore what could have been some other alternatives to spanning tree. This is going to be just kind of one big thought exercise of if we could go back in time into the 80s and we were presented with the choice of spanning tree and what other things could we think of to do, and is there possibly some better mechanism than using spanning tree? So the first option I thought of was, well, what if we just get rid of bum traffic? Because if we can get rid of bum traffic, then we don't need a flood, and then we don't need spanning tree at all. But if you start thinking through this, you'll realize that I don't think it's very feasible to get rid of bum traffic because broadcast and multicast was inherent to the original Ethernet. As we mentioned in the previous video with the original Ethernet CSMA CD days, any frame sent by any host was received by all devices connected to the shared medium. So broadcast and multicast was kind of happening inherently. There was no devices that were flooding this traffic in order for all devices on that LAN to receive the frame. And so because of this, applications took advantage of these broadcast and multicast capabilities. So if we were to get rid of broadcast and multicast, we would be getting rid of some things that are very useful. And while I started thinking through what applications are using broadcast and multicast, they mostly just have to do with auto discovery. So we've got ARP, this auto discovery of a host's MAC address given a known IP address. We've got DHCP auto discovery of a device's IP address. For multicast, we've got other auto discovery type of things like CDP and LLDP, auto discovery of devices connected on that link. Even routing protocols like OSPF and EIGRP are multicast for layer 2, and you auto discover all your neighbors on a shared LAN. So if we were going to get rid of this, we'd have to say, okay, well, no more auto discovery. Every single device has to have a static ARP entry. Every device has to have a static IPs, no more DHCP. And I think this is just not a feasible idea. But we could say, well, what if we simply allow broadcast and multicast, and that uses maybe the spanning tree, but we stop flooding unknown unicast, and unicast could then use all links, and we'd have like this separate topology. Well, the problem is that we have to flood unknown unicast because switches are learning MACs in the data plane. So in order to stop flooding unknown unicast, we would have to have some kind of control plane mechanism for learning MACs on these switches. Essentially we'd start turning the switches even more into layer 3 forwarding devices, and they would be like routing MAC addresses. So we'd have something like a host-to-switch protocol where the host advertises its MAC address to the switch, and then the switches advertise MAC addresses between each other. And now you're not flooding unknown unicast anymore. You're doing layer 3 behavior of if destination is unknown, you just drop it. But back in the 80s, when transparent switching was invented to solve that problem of connecting multiple Ethernets together, the main requirement was that no change to the host and how Ethernet operates was to be done. So that's not very feasible either. But another option could be, well, what if you just leave data plane learning on, but you also don't flood unknown unicast? So switches will just have to have seen a frame from a particular host in order to send it to that particular host. But then we would get into this silent hosts problem where, let's label this device A and this device B. Let's say this device A has a ARP cache entry for device B that's a 4 hours timeout. So it's been maybe 30 minutes into this timeout. But there's been no flow between these two devices. But this device might be communicating to other devices on its LAN and these devices here. So these two switches have that device's MAC and their CAM tables. But this switch has aged out this device B's MAC address because it's been more than 5 minutes since there's been any flow between this device and any devices in this building too. So what would happen if this device then goes to send something to device B? Well, it still knows it's MAC because the ARP entry is still cached. It sends the frame, let's say a TCP SYN, and it'll just age out and age out and age out. And then, the network administrator will have to take a look at this and start troubleshooting this, and they'd log into the switch and say, oh, okay, yeah, that MAC address is not in the CAM table anymore, it aged out, so what would you do to fix this? You would go into this PC and then start pinging stuff and building two so that this switch learns that MAC address. I mean, that is so much hassle and, completely unscalable. As you get more and more flows and more devices, you have to keep doing this. So unknown unicast flooding is the better option. So we've kind of exhausted this idea of getting rid of bum traffic, and we've kind of proved why we do need bum traffic. And if you kind of flip this problem on its head and look at it a different way, you can kind of view it as, well, Ethernet already inherently, CSMA-CD Ethernet, everything was flooded. So the switches, by default, can flood everything. And then as an optimization, we say, well, if the switch has learned this MAC address on a particular port, then it will forward frames destined to that MAC address only in that particular port. So we were kind of starting at this baseline of flood everything, and then just add this one optimization of MAC address learning with this relatively short timeout of 5 minutes or something in the CAM table. So now that we've kind of explored the role of broadcast and multicast applications on a layer 2 Ethernet LAN, it might be interesting to look at, why doesn't layer 3 need a spanning tree protocol? How does layer 3 handle loops? Because if we just take this topology where this particular link is blocked by spanning tree, and we change these 3 switches to routers, well, now we can use all of these links. Well, why exactly is that? Why don't we need a blocking the links? Well, there's a few reasons for this. If we look at the 3 different types of traffic that switches flood, we can kind of go through each one individually and see how layer 3 handles it. So for unknown unicast, there is no such thing as unknown unicast for layer 3, because with routing, forwarding is based on learning prefix reachability in the control plane, not with data plane learning. So any destination that a router does not know, it is simply dropped. The router has to learn routes in its control plane through some mechanisms, such as static routing, routing protocols, things like that. You can imagine that it would not make sense for routers to forward unknown or flood unknown unicast traffic between themselves, because that was never something that needed to be done, because routers are connecting different networks to each other. Whereas switches were being transparently placed into Ethernet that already supported the reachability between all hosts on the shared medium in the first place. So next we can look at broadcast, and for layer 3, also broadcast is not something that can be used, that layer 3 never supported. You can imagine that it would make no sense at all for a single host on the internet to be able to generate a packet that was broadcast and was flooded and copied to every single other host on the entire internet. That just wouldn't make sense. Because layer 2 and layer 3 have, this very different scale. Layer 2 is one local area network, whereas layer 3 is connecting, these local area networks together in a much bigger network. So because layer 3 has never supported broadcast, auto-discovery type of things for layer 3 have been created using different means that rely on unicast. So like the main auto-discovery at layer 3 is DNS, discovering an IP address given a known name. And that just uses unicast. The host learns its DNS through servers through some means, DHCP or statically, asks the DNS server for a resolution via unicast. But multicast is the interesting type of traffic for layer 3 because layer 3 does support multicast, but it's not something that's supported inherently by default, whereas Ethernet supports broadcast and multicast inherently by default. Switches have to too. Switches, they wanted it to just be completely plug and play and transparent and to support broadcast and multicast functionality. Whereas layer 3 was never, from the get-go, supporting multicast. You need to add some things to be able to do this. So what we use today is mainly PIM to support multicast routing. And PIM is kind of interesting to look at because comparing multicast routing to spanning tree, there's actually a lot of similarities. But with spanning tree sparse mode, this topology I've got here, we've got a rendezvous point, and then we've got receivers. And so we build a tree, and similar to spanning tree, we have some root of the tree. And then as we go out, these branches of the tree to leaves. And in this case, the leaves are the receivers receiving this multicast traffic. And this is just a one-way distribution tree. So with spanning tree, with layer 2, bump traffic is flooded in any direction on this tree, up and down. But with PIM sparse mode, these trees are just one direction. You just forward traffic from the root of the tree, either the source or the rendezvous point, down towards the receivers. And because of this, we actually don't need a spanning tree, and we use something else for loop prevention, which is we use an RPF check. So PIM relies on the IP unicast table, and it assumes that the IP unicast routing table is itself already loop-free. So given that the unicast routing table is already loop-free, then we can say that the reverse direction of that traffic is loop-free, and hence we do a flood or a loop prevention based on the RPF check. So each router just looks at the root of the tree and says, what is my best route, my IP unicast route to that root of the tree? If there's multiple ECMP paths, you just choose one through some tiebreaker. And then that one interface is my RPF interface, my reverse path forwarding interface. And I'm only going to accept multicast traffic incoming on that one interface. And that's the loop prevention mechanism. So this router here has determined this RPF interface to the RP is this particular interface. It can only receive multicast traffic for a particular group on that one interface. And then traffic is flooded and replicated out all interfaces in the outgoing interface list. So this is only a one-way tree because we're looking at the reverse direction of the unicast traffic, which is the other direction. But PIM binder is actually a very interesting case because in PIM binder, you actually literally do a spanning tree on top of the with PIM. So with binder, we want two-way traffic. We end up doing this this optimization and state trade-off where we say for some particular multicast group, there's going to be so many senders and receivers that there's going to be too much state in PIM. So if there's just hundreds of receivers that are also senders, we're just going to have hundreds of groups of these S, G states, and we don't want that. So what if we just make one tree that's bidirectional, so everybody in this group can send up and down the tree, and then we can just get rid of all the state. We only have one particular state entry. But we've traded off that state for less optimization because now traffic is going to have to go through the RP in some circumstances. So if we just take, so now we can no longer use the RPF check because now we want to do bidirectional traffic on this tree. And the loop prevention mechanism right now is just, I'm only accepting traffic on my RPF interface. So if we want to have one tree in this case, like let's say we want to take this one tree here and say, well, the senders can also, the receivers can also send up this tree too. Well, this device here tries to send to this group, it's not going to be accepted because it's not the RPF interface. So we need some other mechanism here for PIM binder to allow traffic up and down the tree. And that's where we literally just do spanning tree mechanisms to be able to create a spanning tree. and forward, up, and down the tree. So if we take from the RP down and just switch all of these routers with switches, replace them with switches, and let's say this device here is the root bridge, and here's how the spanning tree election process would work with designated ports, root ports, and then this port is left as a blocking port. So now if we go back and change these back to routers with PIM-BITR, literally the same exact thing happens. Instead of a root bridge, we have a rendezvous point. Instead of root ports, we have a PIM-BITR upstream port. That's this U here. The election mechanism is the same. Each router looks at its best path to that route and says that's my upstream port. That's my one upstream port. On every link, instead of a designated port, we have a designated forwarder. And indeed, the routers do, through PIM, negotiate and advertise who has a better routing metric to the route, to the rendezvous point, to determine which router is going to be the designated forwarder on that link. And then any ports that are left, you make non-designated forwarder, which is like spanning tree blocking. So now we've done basically spanning tree, but with PIM, and built this spanning tree topology for this particular group, and now we can flood up and down the tree because it's now loop-free thanks to this spanning tree mechanism. So it's kind of interesting to consider that nowadays people view spanning tree as this kind of bad thing that is blocking redundant paths and is giving you unused bandwidth in your network. But we don't really say the same thing with PIM-BITR. I mean, we acknowledge that, yes, there's this trade-off here, especially with the fact that traffic, from this host to this host is having to flow through the rendezvous point instead of just going directly because we've built this spanning tree topology. But we don't really say that it doesn't seem as bad as spanning tree for layer 2. And that's primarily because PIM is this multicast overlay on top of the IP unicast routing topology. Because PIM relies on the IP unicast topology to build trees, and only multicast traffic is using these trees that are built through PIM. With spanning tree, all traffic, including unicast traffic, is using the topology that's built by spanning tree. Whereas in this case, unicast traffic is still flowing through this link. So it's not really a problem as much as spanning tree is for layer 2, because we're just using this as an overlay for multicast, a particular multicast tree. So now let's explore another option as a alternative to spanning tree, which is what if we just put a TTL in the Ethernet header? And this is something that I think is actually a myth. And some training material will say, oh, well, if they just had a TTL field in the Ethernet header, then we wouldn't need spanning tree at all. That would have been nice if, as if the inventors of Ethernet just weren't smart enough to think of this. But even if we did have a TTL field in the Ethernet header, we would still need spanning tree. And I found this course from UC Berkeley, computer science course on networking, that I thought was kind of interesting, that they're talking about spanning tree and the problem of layer 2 loops, and they say, how do we solve this problem? We should delete redundant links so that the topology has no loops. And then the learning switch approach will work just fine with no broadcast storm. So here they've deleted this link between R2 and R4 using spanning tree. And it says, note, another solution might be to add a TTL field to each packet so that the packet expires before being forwarded too many times, or after being forwarded too many times. And unfortunately, the Ethernet header does not have a TTL field, so this solution can't be implemented. And this seems to insinuate that, oh, well, if Ethernet just happened to have a TTL field, we wouldn't need to do this spanning tree stuff and block links. Well, first of all, it's not really Ethernet's fault that it doesn't have a TTL field, because Ethernet was inherently a link layer technology that is for hosts communicating on this shared medium. It was never intended for Ethernet frames to be forwarded from hop-by devices. So it wouldn't make sense to put a TTL field into Ethernet. Why would the inventors of Ethernet put that TTL field there? It'd just be unwasted space. But second of all, even if we had that TTL field, if we can somehow retroactively add this TTL field to Ethernet and upgrade the Ethernet drivers of all Ethernet devices in the world, this still wouldn't solve the problem. Because let's go back to our switch topology where this link is blocked. And let's say, okay, we're going to put a TTL field to Ethernet. Let's do some value like 32. So a maximum of 32 switch tops that a frame can be forwarded through. We'll unblock this link. We'll turn off spanning tree. So now we've got this loop that's formed. Would we as an industry accept this as a solution? And I would say definitely not. Because let's say this PC is trying to do an ARP resolution for this host here. It sends the ARP. That ARP is now going to get flooded and go loop 32 times before it finally expires. So would we just allow all bump traffic to flood over and over and over, but just be bound by the the TTL number that we set in the frame? Not only that, but while this ARP frame is flooding 32 times, this switch here, its cam table is essentially getting corrupted because every time this floods in this direction, it's learning the source MAC address of this PC on this link. So now any unicast traffic, let's say this host to, or actually we should change this to the full duplex one, but for this host to this host, it's sending out this link, and there's packet loss. So not only are we allowing traffic to flood over and over and over just for a certain amount of times, but we're allowing, while that bump traffic is flooding, for the cam table to be corrupted until this host sends a frame after that. So of course this is not a solution. But a TTL field would be useful for the case of microloops, because spanning trees convergence timers are extremely conservative. Because with spanning tree, you never, ever want to get into a situation where there's even a moment, a millisecond of looping. Because even if there's a brief moment of looping, it has a possibility of completely bringing spanning tree down. Because if you have this brief moment of looping, you exponentially flood and replicate the bump traffic, and it can saturate the links to the point where now your spanning tree BPDUs end up getting dropped, and you prevent spanning tree from even converging. So that's why spanning tree's original timers are so slow. You go through multiple stages of sending the topology change notification, waiting for all switches to hear about that, and flushing their MAC address tables, and links go through listening first to reduce unknown unicast flooding, as on the one hand, but also just to be extremely careful that you never get into this microloop situation. And the TTL field in IP is actually extremely useful for microloop situations when you get microloops with link state protocols like OSPF and ISIS. We allow this to happen because the TTL field takes care of it. So a microloop happens in a link state protocol when there's some link failure somewhere in the network, and that change is flooded in the LSA or LSP. And routers that are closer to that event will process that LSA or LSP more quickly than routers that are further away in the topology. And you'll have a situation where one router says, okay, I've processed this LSA, updated my forwarding tables, and now this router is my next stop for this prefix now. But this router here has not yet received the LSA, or has received it and is still in the process of running SPF and updating its forwarding table. So this router still thinks, oh, this router is still my best path. We're in a state where the topology hasn't fully converged yet. So while this is happening, these routers are looping this packet between each other until finally at some point all routers have converged. And this microloop is very brief, maybe 100, 200 milliseconds. But generally we allow this to happen without any problems because the TTL field takes care of this. The packet is eventually expired, and then within 100 milliseconds, the entire topology is converged. I thought it would be also interesting to point out that the TTL field is also useful in some designs where it's not a microloop, it's actually a permanent loop because of how the routing works. So in this diagram, we've got a L3 VPN MPLS network. And this customer has this one hub router that's connected to an internet router connected to the internet. This hub router has a static default route pointing to the internet router. And the internet router has a static 172.16/16, essentially a summary route that's statically pointing to the L3 VPN hub. So you might have seen networks like this where, let's say, the MPLS circuit for this router here goes down. You might be on some other network, some other router here at some other site, and you might just do a ping-t to the 2.1 address because you're curious, okay, I want to see when this circuit comes back up. And you might have noticed that your replies don't time out. You might get a TTL expired. Well, that's because the hub no longer has the route for 2.1. So this traffic is getting forwarded to the hub, and the hub is just following its default route to the internet router. But the internet router has a this summary route pointing back to the hub, so there's this loop right here. And this loop is only broken by the TTL field in the IP header. And generally, this doesn't saturate the link because it's not like there's a flood of traffic to this network. Maybe there's some TCP SYNs trying to get through, but those just time out. There's not actually a session that's happening where there's a lot of traffic going on this link. There's just very little traffic pings, TCP SYNs, etc. that just they get forwarded back and forth 255 times, and then they stop. And of course, you can prevent this by just adding a null zero discard route for that summary on this hub, and you no longer have that problem. But there's a lot of networks where they're configured like this, and nobody really cares because the TTL field just breaks that loop whenever this kind of a loop happens. So we've explored getting rid of bump traffic. We can't. Putting a TTL field in the Ethernet header, sure, it would help with micro loops, but that doesn't solve the problem. We still need spanning tree. Well, what if we do split horizon? And this is the mechanism that VPLS uses to do loop prevention. So with VPLS, the PEs are essentially like layer 2 bridges and MPLS routers at the same time, right? So they're doing bridging and also participating in the MPLS network. The PEs don't need to run spanning tree between themselves. And why is that? Well, it's because the MPLS architecture, because it's using layer 3 as the underlay, there's always a full mesh of pseudowires between all the PEs. So we can do this very simple split horizon rule where instead of running spanning tree and having this complexity there, we just simply say, if a PE receives a bump frame on any pseudowire, then it doesn't need to send it out any other pseudowire because it can assume that all the other PEs have already received that bump frame too, because we've got this full mesh of pseudowires. Similar to IBGP split horizon, right? You need a full mesh. It's kind of flipped around there, the logic there, but you need a full mesh of IBGP because routes aren't reflected from IBGP peer to IBGP peer. So can we do that with layer 2 switching topologies? We could, but I think it doesn't make sense. So if we go back to our switch diagram here, we can roughly replace the pseudowires in VPLS with layer 2 trunks. So we can say, okay, well, we're going to have to require that all switches have a full mesh of layer 2 trunks between each other. That already limits the topologies, and that already kind of doesn't make sense. But let's go further with this and see what happens if we do this. So we'll unblock this link. No, we're not running spanning tree anymore. We're just doing this this split horizon for loop prevention. So on all the switches, we say, if you receive a bump frame on any trunk, don't send it out any other trunk. And we happen to have a full mesh of trunks here. So that would work when all of the links are up. But the other problem, besides having to require a full mesh of trunks between all these switches, is that it doesn't allow for any redundancy. Because let's say this link actually does go down. Now this host communicating to this host has to go through this switch at the top. But the switch still has a split horizon rule. This switch is still saying, if I receive the bump frame in this link, I'm not going to send it out this link. So now we've broken reachability for bump traffic between these two switches. Well, why is it that if we make these routers and run VPLS, why does it still work when a link goes down? Well, that's because VPLS is an overlay on top of the IP-MPLS underlay. So if these were IP-MPLS devices and these were all three PEs, if this link goes down, the pseudowire between this PE and this PE is still up because it's routed. So it routes through, as long as there's any kind of layer 3 reachability between any PEs, the pseudowire is always up. That's why we can use split horizon in VPLS, because we've got this underlying overlay topology. And so that actually brings us to the last idea that's actually the best idea, which is, what if we do a link state protocol in this switched network between the switches? And so, because to back up, with spanning tree, it's really a distance vector mechanism. Uh, Switches advertise their cost to the root bridge and pass this hop by hop. So none of the switches have a full topology view. The switch only knows reported costs from its neighboring switches. It's essentially like RIP, but instead of advertising some IP prefix, you're advertising the root bridge ID instead of a IP prefix. So what if we do instead some link state protocol so that all the switches can have a full view of the topology? This way we can do things like ECMP and use all paths, but we would also have to add some kind of a overlay mechanism so that we can kind of tunnel traffic from one edge switch to another edge switch. That way we can use ECMP, because we could say, okay, traffic from one edge switch, now that's look at my link state database to view all the possible paths, etc. And then for any flooded traffic, that's a different case. We can build multiple basically spanning trees, multicast distribution trees, kind of like PIM, and just flood that traffic down those distribution trees. So there's multiple protocols that came that use this idea, and two of the famous ones are TRILL and shortest path bridging. So these were both created around the same time, around 2006, and they're both very similar. TRILL was created in the ITF through with Radia Perlman as one of the authors, and shortest path bridging was created through the IEEE. They both use ISIS as the link state protocol. This is because it's a layer 2 switch network, so ISIS decouples the topology building from IP. So you can run DEC, IP, IPv6, etc. on ISIS, and you can also do layer 2. So it's literally routing at layer 2. Both of them have some kind of encapsulation. So with TRILL, it's a MAC and MAC encapsulation, and it's a 6-byte header that's added, and this tunnels the traffic between the edge devices. And with shortest path bridging, it uses provider backbone bridging, PBB. So this is a larger encapsulation overhead than TRILL. But shortest path bridging has some other advantages, like it allows for completely symmetric paths one way and back the other way through the edge switches. It also allows for use of the existing Ethernet OEM tools. Another difference is that TRILL adds a TTL field to the MAC and MAC encapsulation. This handles microloops that happen with ISIS, as we were talking about, that link state protocols are susceptible to microloops. Shortest path bridging had a different concept, a different idea, in that you shouldn't need a TTL at all. So instead, some argue that they've overly complicated ISIS to be able to remove the possibility of microloops completely, so that they didn't need to do a TTL field in their overhead encapsulation. And it's probably because provider backbone bridging does not have the TTL field, so that explains it. And there were different vendor implementations of TRILL and shortest path bridging, but they ended up being kind of proprietary, especially for TRILL. So with TRILL, Cisco Fabric Path was one of the popular vendor implementations. But these vendor implementations were usually some kind of proprietary data plane or control plane, along with the standard TRILL data plane or control plane. Shortest path bridging, I've seen the implementation seem to be a little bit more open, but generally customers that are using this don't mix and match devices. Some popular implementations are Extreme / Avaya Fabric Path, and I believe Alcatel-Lucent had an implementation of shortest path bridging. And from what I've seen, shortest path bridging is more likely to be in use today than TRILL. So this is a just kind of an overview of shortest path bridging. So you've got some kind of arbitrary layer 2 core switch network here with like a kind of a partial mesh. And spanning tree is going to block a lot of these links, and traffic is going to be non-optimal because it's going to have to flow through the root bridge in certain cases. So it's just showing you these are all the problems with spanning tree, and all the bridges or switches in the core and the transit path are learning max for all the customers on the edge. With shortest path bridging, it really takes these VPLS concepts. VPLS was already invented, by the way, at this time. So really the people that were authoring this were for sure influenced by VPLS, and uses this kind of overlay underlay idea that you do some kind of encapsulation between edge devices or PEs or the these edge switches here. And then the core only has to learn the max of the edge devices, analogous to in MPLS, VPLS. The core only knows IP reachability to the PEs, doesn't care about the customer max in the layer 2 VPN. So you get the same benefits. You can use all of your paths, things like that. And some people still today say shortest path bridging is actually better than running like a VPLS service or L3 VPN, because they'll say, well, with that, you've got all these different protocols. You've got your IGP, and then you've got your MPLS or LDP or SR, etc. And then you've got maybe traffic engineering with RCPTE and stuff. And then you need BGP to do the control plane. And they say, well, you can get rid of all of this and just do this all with ISIS. And actually with ISIS, with both TRILL and shortest path bridging, what happens is that some of the control plane information, like what VLANs our switch is participating in and things like that, that's actually advertised within ISIS. So you're kind of just doing everything, dumping everything into ISIS. But these days, most people view doing an IP routed underlay as the better idea, the less complex idea. So, of course, nowadays, we've basically settled on EVPN VXLAN as the solution to this, kind of taking all these ideas, all the best ideas of doing underlay and overlay, by doing an IP or some kind of link state-based underlay, you get the advantage of being able to use eSCMP paths, etc. And then you just overlay the layer 2 on top of that with some kind of encapsulation. And it's interesting to consider why EVPN VXLAN won out. Why aren't we just using shortest path bridging everywhere? Well, I think there's a few points here. One is that EVPN is much more scalable. We're carrying control plane information in BGP with EVPN instead of within the link state protocol. BGP is a little bit better to handle very high scalability of control plane information. Another is that TRILL and shortest path bridging are auto-forming this single-level ISIS domain. And with EVPN VXLAN, we're using any kind of arbitrary IP routed underlay. So you're free to do whatever you want in terms of IGP areas and things of that nature to scale even higher. Another thing in EVPN VXLAN's favor is that VXLAN runs directly over IP. It's just a UDP encapsulation, so all you need is IP forwarding devices in the core, and that is basically anything today is going to support that. It's all you just have to support IP routing and whatever IGP you're running. Whereas with shortest path bridging, you need in particular the provider backbone bridging encapsulation. So maybe you need this special support from switches to be able to do this, and not all switches are going to support this. Another advantage in EVPN VXLAN's case is that you only need to run the control plane at the edge nodes, similar to PEs running BGP. You can have like a BGP free core in MPLS. With shortest path bridging, all switches are participating in this, and all switches are running ISIS and learning all the control plane information, etc. So even though these switches are not learning customer MACs because there's that encapsulation, they are having to process all the control plane information that's being flooded into ISIS. And then another point in favor of EVPN is that it allows for easy multi-homing. You can't, do this really with any other layer 2 technology, except for maybe multi-chassis lag, but EVPN is like a vendor-neutral way of doing multi-homing. And EVPN also allows you to learn MACs in the control plane, allow remote MACs. So with all of these other overlay technologies, VPLS, TRILL, shortest path bridging, all of these devices at the edge are still learning the remote MACs through the data plane by receiving the bump frame on a particular pseudowire, so the PE knows, okay, I received that MAC from this remote PE because I learned it in the data plane. In this case, through the encapsulation, saying that, okay, this encapsulation was from this particular switch on the other side of the network, so now I've learned that MAC address. Whereas with EVPN, you get rid of data plane learning from remote MACs, and you just do it in the control plane. And lastly, to wrap this up, we should look at how flooding works with this underlay overlay mechanism, because we've essentially turned, by doing overlay and underlay, we've have this underlay that's completely routed and there's no flooding at all. It's just IP routing. But we still have to support flooding for layer 2. We're still supporting Ethernet flooding between these sites. Typically, what I see is that the most frequent case is that you just do ingress replication. Just like VPLS, if your buffering needs to be flooded to all of the participating PEs in a particular L2 VPN VPLS service, you just replicate that traffic to all PEs. But some of these overlay underlay mechanisms have some optimizations there that you can have multicast trees, in an EVPN's case, that are built with PIM, with shortest path bridging. These are built with ISIS at layer 2. And you just build different distribution trees that are sourced at each of the nodes that are participating in this L2 VPN service, and then you flood it down that, so that the nodes, you're getting the multicast optimization in the underlay instead of having to do ingress replication. And those are basically the two choices that I've seen for handling bump traffic. And of course, while you've gotten rid of spanning tree in the core, you still probably want spanning tree on your edge nodes. So basically, you can have every single edge device just be a single device spanning tree topology, where that one device is the root, and you run, port fast and BPDU guard on the switch ports, because you still have all these switch ports, and you still have the possibility of customers plugging these switch ports into each other and creating loops. So while you've gotten rid of spanning tree in the core, I think it's still a good idea to handle loop prevention still on that single device as well. And it's interesting to note that we've gone from, this very early days of how do we connect these separate Ethernets? Oh, should we do a learning bridge or should we do just routing? And we decided, okay, we're going to do this learning bridge and deal with the flooding by doing spanning tree and stuff. And then we've kind of gone back to saying, let's just do routing, but actually let's do that as the underlay and then overlay the layer 2 on top of that. And I wonder if you would say that nowadays, in any greenfield network that's going to support layer 2, that's stretched between, sites or racks, etc., that should you just always by default do underlay overlay? Should you just always do layer 3 underlay and overlay the layer 2? Is that the cleanest way to deal with it? Perhaps. So I think that covers it for this video, and in the next video we'll talk about spanning tree in more detail, how the algorithm works, looking at it from a graph theory point of view, and all of the considerations we have to take with spanning tree and all of the things that spanning tree is lacking that makes it difficult to work with, especially from a service provider perspective.